Hi guys, this is section 3.4. We are continuing on with all of the characteristics that we're finding using the first derivatives and the second derivatives. The end goal being that we are going to be able to draw these really crazy functions without using a calculator, but simply by identifying their characteristics and analyzing the effects that derivatives have on the graphs of f of x. So we are on concavity and the second derivative test. If you recall from 3.3, we were doing the first derivative test. So when we found the first derivative and we set it equal to 0, we know that that is a critical value, a point where there is either a max or a min value on the graph of f of x. From that, we were also able to determine the exact coordinates of the max or the min value. Here, when we are using the second derivative test, we are going to be able to determine concavity and possible inflection points. Concavity is how a function curves. For example, if you look at the graphs on page 184, figure 3.24 A and B, we've got a couple of graphs there, and where we've got points on the graph, if we can draw the derivative, which is the tangent line, at these given points, we can see that the slope tends towards positive. So that means that the function is concave up there because the slope of the tangent is positive. Likewise, on the second graph, when we draw tangents to these points here, the slope of those tangent lines tends towards negative. So the function is concave down. So we see here, if f prime prime, the second derivative, is greater than 0, the function is concave up. If the second derivative is less than 0 or negative, the function is concave down. And what we're going to do is we are going to construct a table, much like we did in 3.3 to determine increasing and decreasing. We are going to construct a table and do almost the exact same procedure using the second derivative, where the second derivative is equal to 0, and then put that into a table. And if we get a positive number in our test value, the function is concave up there. Conversely, if we get a negative value at a critical number in the second derivative, the function is concave down. Now, when concavity changes from up to down or from down to up, there may also be a point of inflection. And a point of inflection basically looks like a squiggle. So on that graph, this is the graph of, as closely as possible, y equals x cubed. So you can see that little squiggle there at the origin is a point of inflection. The graph is concave down on this portion and concave up on that portion. So when the concavity changes, there may be a point of inflection. Okay, so that's what we are going to do. We're going to look for concavity. Now, the second derivative, of course, requires quite a bit more algebra than the first derivatives do. So knowing that we already know how to do all of the rules for derivatives, these are going to be the means of how you get these derivatives simplified, because the class as a whole has chosen the multiple choice tests. Remember, if you're choosing from multiple choice, your answer needs to match one of the options. And sometimes your answer is not going to match the options, even though it's there, because you're not sure how to completely simplify a derivative because of the algebra. And that's what these first couple of examples are going to do, is get into the algebra and how the derivatives get simplified using your algebra 2 skills. So On page 185, notice example 1 says to determine the open intervals. Okay? Open intervals means that we are starting from negative infinity, breaking up the intervals with our critical numbers, and heading off to positive infinity. Okay? Now, of course, in order to determine the second derivative, we need to find the first derivative first. So the function is given as y equals 6 over x squared plus 3. Seems harmless enough. So that is a quotient, so we'll follow the quotient rule, which means that we're going to take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which is 2x. And that is all over the denominator squared. Okay, now before we get to the second derivative, we are going to clean up the first derivative. So obviously that goes to 0, and we are left with the fact that y prime is equal to negative 12x all over the denominator squared. Okay. Now, eventually what's going to happen is that we're going to need to take the denominator and find its derivative. That is the chain rule. So before we get to the point of needing that, let's do our u prime, f prime u thing. So u is going to be our x squared plus 3. U prime is 2x. F of u is taking the u function and squaring it, and f prime u is 2u. So we've got u prime times f prime u, and that is going to be 2x times 2 times the quantity x squared plus 3. Okay, so that is our chain rule, and that can be simplified to 4x times x squared plus 3. Okay, so we're going to take the derivative of the derivative. In other words, the second derivative. It is also a quotient. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. All over. Wow, that is a mess, isn't it? All over. Now the numerator has already been squared, so squaring a square gives us to the fourth. Okay, so everybody should be okay. Now, the calculus is done. The rest of it is this algebra. So we'll start with the negative 12 times x squared plus 3, quantity squared. And of course, because this quantity is squared, remember, you cannot distribute the negative 12 in. Definitely breaking all of your rules. And then minus, and I'm just going to put that in brackets, you've got a negative 12 times a 4. So that is going to give you negative 48 x squared times your x squared plus 3. Now, you'll see why I'm leaving the negative 48x squared out and not distributing it into the x squared plus 3. So we're going to move on here, y prime prime. So we're going to leave the negative 12x squared plus 3 squared plus 48x squared times x squared plus 3 all over the x squared plus 3 all to the fourth. So what you should notice now is that you've got an x squared plus 3 right there, and you've also got one right here. Another GCF that can be pulled out is that negative 12. So that's how the simplification is going to continue. We're going to pull out a negative 12. We're going to pull out a negative 12 along with one of the x squareds plus 3. And when we do that, we're leaving one of those x squareds plus 3. And when we take a negative 12 out of a positive 48, we end up with a minus 4x squared. Okay. So now you should see where this is going. We are going to get a negative 12 times the x squared plus 3 times negative 3x squared plus 3 all over an x squared plus 3 to the fourth. So we continue with the simplification in that this x squared plus 3 on the top cancels out one of those on the bottom. And then we are left with the fact that y prime prime is equal to negative 12 times the 3x squared plus 3 all over x squared plus 3 all cubed. Then we can distribute in the 12. So this is kind of like distributing and then pulling back out again. But negative 36x squared minus 36 all over x squared plus 3 all cubed. Now, the thing is that this might seem like a little bit of a pointless, tedious thing. But remember, we have to be able to set this second derivative equal to 0. Now, if you look, there is no way that you're going to take that right there and set that thing equal to 0 and solve it for x. It's just not going to happen. That's why all of this algebra, tedious and totally annoying, I get that, but that's why it's so important. So the final simplification will be pulling out a 36, and then we will be left with x squared minus 1. Okay, and then we have the denominator. So remember that the second derivative is equal to 0 where the numerator is equal to 0, which are critical numbers. And remember also that it is undefined where the denominator equals 0. Those are critical numbers as well. But because we've got an x cubed plus 3 in the denominator, there is no place where that function is undefined, meaning that there are no vertical asymptotes. Okay? Because remember, the vertical asymptotes exist where the denominator of a fraction equals 0. So if there's no points of vertical asymptotes where there's a discontinuity in the denominator, when our concavity changes, possibly from up to down or down to up, because the function is not broken where the second derivative equals 0, that might be a point of inflection. Okay, so going with that, we know that the only place that this function is equal to 0 is where x squared minus 1 is equal to 0. 36 is never equal to 0, so we don't have to worry about setting the 36 equal to 0 because 36 doesn't equal 0. So we take the numerator, and we know that x squared minus 1 is equal to 0, where x is equal to -1 and +1. Those are the critical numbers in the second derivative. On an open interval, we will go from -infinity to x to -1, then from -1 to +1, and then from +1 off into positive infinity. So this is where your second enter thing is going to come in very handy. F prime prime sign, and then conclusion. So we don't have to worry about doing this by hand. So our test numbers here could be -2, 0, and +2. And remember, all you care about is the sign. You don't care about what number comes along with that. You only need the positive or the negative. And when you throw a -2 into the second derivative, you get a positive number. When you throw a 0 in, you'll get a negative, and 2 will give you a positive. So the conclusion is that the concavity is up from -infinity to -1. It is down from -1 to +1, and up again from 1 to infinity. So we can find out what those points are by plugging in -1 into the original function and getting the points of concavity. Okay, you know that it'll go from up to down right there at -1, and then it'll go from down to up right there at +1. We just don't know yet what the graph looks like in its entirety. All right, moving on, we are going to do the exact same thing with example 2. Example 2 on page 186 says determine the open intervals in which the graph of the given function is concave up or down. Okay, so again, we've got another quotient. That's what happens when you're left-handed. So y equals x squared plus 1 over x squared minus 4. So finding the first derivative, we use the quotient rule, which is x squared minus 4 times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Doing some simplification here, we have 2x cubed minus 8x. And then after the minus there, we will have minus 2x cubed and then minus 2x. And we have some things that can simplify there, thankfully. Make our job a little bit easier, okay? So moving forward, we can see that the 2x cubes cancel each other out, and we are left with y prime is negative 10x over x squared minus 4 squared. Now, again, in finding the second derivative, the denominator is going to require the chain rule. So let's go over to the side and we will work the chain rule. So when we need it, we have it to plug in right away. So our u is going to be x squared minus 4. U prime is 2x. F of u is u squared. And f prime u is 2u. So u prime times f prime u is going to be u prime is 2x and f prime u is 2 times the quantity x squared minus 4. So we'll just simplify that right now to 4x times x squared minus 4. And the reason that I'm going to leave it like that is because in our denominator we have an x squared minus 4, and maybe we'll be able to use that for some simplification. Okay, so now we will move on to the second derivative. Y prime prime is equal to the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. That's a lot of parentheses. Okay, well, we'll simplify it. And then the denominator is already squared, so when we square it, it is now to the 4th power. So we're just going to clean this up. So the calculus is done, and now is the big pain, the algebra, okay? So we're going to simplify what's inside that bracket. And 10x times 4x is a negative 40x squared times x squared minus 4. And that's all over the denominator, all to the 4th. And then, of course, simplifying that, is going to give us plus the 40x squared, times the x squared minus 4. So see, what we're going to do with this is we're going to pull out a negative 10. We're going to pull out a negative 10 and 1 of the quantity x squared minus 4. Okay, and when we do that, we will be left with an x squared minus 4 and a minus 4x squared. Okay. So now actually the parentheses here don't need to be there. So let me rewrite that. X squared minus 4 minus 4x squared. We don't need the parentheses there. It'll be easier to not. So now I think you can see where this is going, because what's going to happen is that this x squared minus 4 on the top is going to take one of these with it. So we're left with negative 10 times negative 3x squared minus 4, and we are almost done. And remember, the reason that we need to do this simplification is so we can eventually find where this second derivative is equal to 0. Okay, now x squared minus 4 all cubed, and from there what we can do is pull out a positive 10, 3x squared plus 4 all over x squared minus 4 all cubed. Okay, so we're going to look at this. That is the second derivative. What we're going to do there is find the critical numbers. The critical numbers are where the numerator either goes to 0 or the denominator goes to 0. Well, if you look at the numerator, there's no place there that you're going to find a real number where 3x squared plus 4 is equal to 0. So we're only looking at the denominator. So when you set the denominator equal to 0, you know that x is going to equal negative 2 and positive 2. So that is going to be put into our table from negative infinity to x to negative 2 to negative 2 to x to positive 2, and from positive 2 up into infinity. Okay, So we'll have our test numbers here, our f prime prime sign, again, just positive or negative, and then the conclusion. So we can use a -3, a 0, and a +3. Now, I didn't do this beforehand, so I have to do it now. So we're going to enter a -3 into our calculator. And then what we're going to do is enter the second derivative, which is 10 times the quantity, 3x squared plus 4 over the denominator of x squared minus 4, all cubed. And when you put a -3 into the second derivative, you will get a big mess. Hold on one second, guys. Let me clear. When you plug a -3 into the denominator, you get a positive. Not into the denominator, I mean into the second derivative. When you plug a 0 into the second derivative, you get a negative, and the +3, remember we're using our second enter function, you get a positive. So you are concave up, down, and up. Okay, so having gone through the algebra and finding concavity, we are also going to look at the second derivative test. Okay, the second derivative test is kind of an all-in-one. When you use the second derivative test, you will be able to determine, along with the concavity, the relative max or min. So the last example, we're going to jump to example 4. And it says, find the relative extrema. Now remember, relative extrema is max or min using the second derivative test. So that's a little bit different, not too much, but what we're going to find is that the critical numbers of the first derivative are very important to this process. And thankfully, we don't have to worry about the quotient rule. So notice it says, begin by finding the critical numbers of f. So that is finding the derivative, -15x to the 4th plus 15x squared, setting that equal to 0 and finding your critical numbers. So we can factor out a -15 x squared, -15x squared, and then we would be left with x squared minus 1. So -15x squared equals 0, where x is equal to 0, and x squared minus 1 is equal to 0, where x is equal to negative and positive 1. Those are the critical numbers from the first derivative. Those are going to go into our table now, but we also need to find the second derivative. So the first thing we're going to do is we're going to plug in these x values, these critical numbers, into the original and find the y values. So when x is 0, y is 0. When x is -1, y comes out as -2. And when we plug in an x of 1, we get a y of +2. So those are going to go into our table. Now we will continue on finding the second derivative, which is going to be -60x cubed plus 30x. Okay, so then we can make our table. So it's like we've got this point. Table's a little bit different. It doesn't have intervals in it. We've got the point, -1, -2. That looks stupid. Sorry, guys. +1, +2. So these are the coordinates where y prime was equal to 0. We got the x's, plugged in those x's, and found the y's. So these are all the points, okay? Now, we do need to figure out what the sign of the second derivative would be at -1, +1, and 0. So if you notice in our table, we've got the f prime prime sign. So when x is -1, the second derivative is positive. When f prime prime is +1, we get a negative. And when f prime prime is a 0, we get a 0. And we'll look at that 0 and what the importance of that is in just a minute. So if the second derivative is a positive at -1, that means that it's concave up. Well, let's think about that. If a function, so let's use a very basic function that's concave up, okay? A parabola is very definitely concave up, right? So if a function is concave up, that means that it has a min there. See how the second derivative test gives us not only the concavity here, but it also tells us that there is a min value at -1, -2. So there, likewise, if the second derivative has a negative sign or a negative value at 1, 2, that means that it is concave down. So we have, say, another classic concave down function. Obviously, if the function is concave down here, we have a max value. So we can use the second derivative test and find extrema, which is max and min, along with concavity, all in one table, which is very important because it saves a lot of time. Okay, so you guys know how to reach me. You have the calculus group chat. Work together if you have any questions, and I will let you know what your homework is in just a second. Okay, so I looked on IXL, and there is nothing in IXL that matches up with our concavity. So the homework is going to be strictly book work. So I'm going to write them down along with the verbal. So 1, 7, 11, 15, 19, 21, 24, 27, 29, 31, 33, 35, 37, 39. I guess I could have shortened that and said 27 to 39 odd. And then we're going to jump to 51, 63, and I believe that's it. So what's going to happen is that this lesson, you'll watch the lesson on Monday and then start the homework if you have time. If not, this will also be Tuesday's in-class work, okay? And then it will be due on Wednesday. So how you're going to do that is you're going to have to take pictures of your work and text them to me. There is no other option to get me that homework. It might be an option that the sub is willing to grade it. Maybe. If not, I'll need to get this. It is due Wednesday. I will need to have that communication from you by Wednesday evening. Okay, so you know how to reach me if you have any questions. See you Wednesday. Bye.